being presented as an IEEE Information Theory Society Distinguished Lecture.
Thank you. It's an absolute pleasure to be here. I graduated from this institute just a few decades back, and it's a wonderful thing to be back here. Another thing I want to say is, I want to thank Vinod and everybody else who invited me and organized this so well. It's been wonderful. So this talk is about something I got into as a result of working on information-theoretic measures, which is really something I work on in the context of privacy. And so I'm going to talk about a class of loss functions that I call alpha loss. And I'll make some arguments for why it's a good loss function in the context of machine learning. So the way I'm going to set up this talk is I'm going to present some problems in ML that are new problems. And then I'll segue right into this loss function and its properties and its landscape, its optimization landscape. I'll come back at the end to talk about, with experiments, how this loss function could address these problems in machine learning. Okay? All right. So I think Varun covered this on the first day a little bit. He talked about this. So as you collect more data and you start designing these learning algorithms to make decisions, it's possible to actually fake those learning algorithms by changing data, right? So these learning algorithms are susceptible to what are called adversarial influences, bad examples, or noisy examples. And they're also susceptible to something that exists in all societies, bias, okay? So if your data only comes from some people, or if your data implicitly carries social biases, the algorithms will learn the same thing. So let's talk briefly about each one of these. So he talked about flying pigs, and I'm going to talk about pandas that, if perturbed a little bit, will be classified as a gibbon, even though to the naked eye it looks like a panda, right? And this happens because machine learning algorithms, by definition, are making decisions on, based on some feature space on where this image falls, and if you're at a boundary, if the data is at a boundary, you could just perturb it to fall in the other hypothesis class, okay? So that's what's happening. One of the ways that you want to make these algorithms robust to these attacks is to build it into the learning problem. So you assume that your data X, which comes in, may be perturbed, maybe in L1 sense a little bit. So the kind of algorithm, the model theta you want to learn is really the best, the one that minimizes the loss over the worst case model of the data, of worst case data, right? So there's been work by Madhuri et al. On doing this, and there's been work by Jiantao and a bunch of collaborators on implementing this. But what I'm going to suggest is maybe we can use a loss function approach to do this. But you don't know what alpha loss is, we'll talk about it in a bit, right? In the other context, when you talk about fairness, we had this with its meeting yesterday and so on. One of the things I want to talk about is algorithms can only learn from the data they have. So for example, Amazon tried to make this process of picking candidates for jobs, just do it with the machine, and it turned out literally the machine did not pick a single female resume for interviewing. Okay, so therein lies the bias, right? Here's another simple example. If you use Google Translate, which I use a lot when I travel, and it works in Kannada too, by the way. If you use Google Translate and you write, he is a doctor and she's a nurse, she is a doctor and he's a nurse, and you translate it into Turkish, and Turkish is gender-neutral language. So when you translate it back, it comes out as he is a doctor and she's a nurse. In other words, whatever is the crowdsourcing Google has done to do this translation, that's the kind of existing bias in Turkish language, right? All right, so there's a lot of bias, including machine learning algorithms that are being used to make parole decisions in the United States. And if the data itself is skewed towards certain minority classes, then the machine cannot learn anything more than what the data has, right? So how do you handle these two problems, disparate impact and disparate outcomes? You can take care of societal biases by doing the following. You can say that these kinds of sensitive features such as race and gender should be completely removed from the data set, and you can use GANs to train and do that kind of stuff. And the other thing is when you have a sampling bias like the Amazon data set, one of the things that's been done is, maybe you have only a few females who were interviewed and accepted in the first place. So one way to handle that is to resample from that data set over and over again. You create these synthetic data from that data set, and that's what is generally proposed. What we're going to do is talk about using this loss function to do it, okay? So, we're not diving into the, yes? Right, so generic data augmentation, effectively what you're saying is even though you may have a 90-20, I am a 90-10, I'm just going to up the 10 to a little bit more by resampling within that. Yeah. Well, what we're proposing is to actually boost the 10 in a different way, but we'll talk about that. So the only reason to put up this slide with all this math is to tell you that this work on loss functions came from a completely different work on information measures that we were proposing for privacy. And our goal was, there's a whole bunch of information measures in information theory, and our goal was to say, can you motivate these measures through an adversarial action? And the adversarial action happened to be a class of loss functions. So if you're interested in information measures, you can look at the papers there, but let me talk about loss functions now. Okay, so this is joint work with my PhD student Tyler, my really awesome postdoc Mario, who's now a professor at IMAS in Mexico, Peter Kairuz, who's at Google, and Gautam Dasarathi, who's my colleague at ASU. Right? So here's our loss function. All right? Alpha is your parameter. Y is a feature, and little y is a value that a feature takes. And the loss function operates on the probability of this feature taking the value little y, and this is how the loss function is written. Right? So it takes this probability of this feature, and it raises it to this power, and then this is just a scale factor in the front. All right? So if you, and then the way this loss function is written, you can have continuous extensions at 1 and infinity, and if you plug in alpha equals half, you get what's called a soft exponential loss. If you plug in alpha equals 1 and you do your L'Hopital's and all that, you get log loss, negative log loss. If you plug in alpha equals infinity, you basically get 1 minus the probability of correctly decoding, which is really the probability of error. Okay? So this loss function class recovers some of the well-known loss functions that are used in learning. Okay? All right. What I just said. Okay? So this, if you take the expectation of the probability of error and you do the best decision, you get the 0-1 loss. Okay? All right. So here, what I'm showing you is how does a loss function look like when plotted against that probability that it operates on. Okay? So when alpha is small, less than or equal to 1, this loss function is very convex. And as alpha becomes greater than 1, in the limit as it goes to 1, you get the straight line, 1 minus probability of correctly guessing. Okay? So keep that in mind. How are we going to use this loss function? We're going to be looking at the learning setting, predominantly supervised learning, but here's our setting. We have some features X. Y is a label. You learn on this label, and then you want to predict this label for new data that comes in, right? So the way you learn any learning model or an algorithm is by actually having some metric of goodness for learning, right? So in this case, the loss function we're going to use is alpha loss. All right, so here's our setup. So the relationship between information theory and learning theory is that learning theory, like information theory, is very statistical, right? So you take this loss function, and you're going to evaluate this loss function on, theoretically, on the distribution of the data. So you're looking at the average risk, as this is called. In our case, this is the average alpha risk, okay? So it's over the distribution, joint distribution of X and Y, the label and the feature, okay? All right, so if you actually plugged in this loss function, you can compute this average risk when you know the distribution, and it turns out to be this very nice quantity. Does anybody know what this is called? Yes. It's the tilted distribution, right? So you plug alpha equals 1. We'll talk about it. So what this is saying is the best strategy that minimizes the loss function is really, if you knew the posterior, you just plug it in there, and this is the best strategy to implement, right? Okay. For alpha equals 1, basically this is the true posterior, right? And for alpha equals infinity, you get the map rule. What should the adversary, what do you do? What's the best decision to minimize? You take the one that's the most likely to occur, And that's how you get the 0, 1 loss when you plug it in. So alpha equals half, you get the rule that does exponential. What do you get for alpha equals 0? So alpha equals 0, you become agnostic to the distribution. Basically, it's a uniform distribution. Okay? Okay. What you're saying is you can pick anything and it doesn't matter. Right? So if you plug this in and you look at what the expected risk is, the expected risk turns out to be related to the Arimoto conditional entropy. Okay? All right. So in the interest of time, I'm not going to talk about the information theoretic aspects, and those who are interested can go and look at it. So here's an example where Y, the label we want to learn, is a binomial random variable. Okay? And so here are the values for the binomial random variable, and here is the probability. Okay? So when you plot it like this, so for alpha equals 1, the best strategy when you minimize this loss function is to actually compute this posterior itself. So and that's what you're plotting here. Right? So as alpha increases from 1, effectively what you're doing is you're restricting your output set to a smaller and smaller set. You sort of ignore the low probability events, and you keep restricting it until you get to the map rule, which is only this point. Okay, the most likely event. On the other hand, when you reduce alpha from 1, you actually boost the low likely events. Right? In the limit, you give all possible outcomes the same weight. So this loss function for alpha greater than or equal to 1, especially alpha greater than 1, is going to put more weight on the most likely outcomes. So if your noise is a very low probability event, it's an outlier, it'll probably be ignored. So a lot of outliers will be ignored. In contrast, when alpha is less than 1, you boost those outliers. Okay? And this is why you get the exponential loss, which is what is used in classical boosting, which is when you have weak learners and you boost the algorithm. Okay? All right. So now how do we use alpha loss? In the next 2 parts of the talk, I'm going to talk about how you can apply alpha loss in the supervised setting and what does the optimization landscape look like. Okay? So let's take a simple example. MNIST, this is a data set of handwritten letter numbers from 0 to 9. We'll just take the 1s and the 7s, and our goal is to come up with a way to distinguish between 1s and 7s, right? We want to come up with a learning model that does that. So first what you do is you take the training data, which has the labels with it. So you learn the algorithm based on that, and when the test data comes in, you want to be able to say this is, so you're mapping the 7s to -1 and the 1s to 1, and so when this data comes in, you should say 1, 1, -1, -1, 1, right? Okay. So let's formally set up the problem. Your feature space is X, all right? And your label set is the Rademacher random variable is +1 or -1. Okay, and so Bernoulli, we just stick with the notation of learning theorist here. So your sample is a bunch of n samples of xi, yi, right? And it's a distribution D on xy, right? So the goal of training is to learn an algorithm H that when given xi, yi, it's going to maximize some measure of accuracy, okay? Such that when you get a new sample, it predicts something, and that is as close or as correct as possible. All right, okay. So the optimal hypothesis, it's called hypothesis. The optimal hypothesis is determined by optimizing the accuracy. Now, I keep using the word accuracy. So what is accuracy? The classical notion of accuracy in learning is the probability of error. Okay? It's the probability that you make as few errors as possible. So the hypothesis is H, you count the number of errors you make, and generally you want to minimize them. Right? So when you minimize this, it turns out that the best predictor is your base predictor, which is related to the true posterior in the following manner. You take the true posterior, subtract half from it, take the sign, and this is your optimal strategy to do. This is if you knew the distribution, and this is your decision rule, right? In general, the goal is to actually estimate this true posterior and then plug it in. So that could be a learning algorithm. Okay. So the game is over if you knew how to implement the 0-1 loss. The 0-1 loss is actually the map decoder, right? And we all know that that's NP hard. Okay? So there's been a lot of interest in finding surrogate loss functions for the 0-1 loss in machine learning, in classification. And there have been many, many loss functions that have been proposed. And there's also a really nice theory created by Bartlett and others on what should be the good properties of these surrogate loss functions. Okay? All right. These are some of the papers that have looked at surrogate loss functions. Okay? All right. So before we go to some properties of alpha loss, I do have to talk about, in the context of classification, two notions. What should this function h be, right? You want to predict the label, but you can do it in two different ways. You can take your input x, you can map, you can come up with some decision that's over the set of all reals, you take the sign of that, and then voila, you predict that's your y. So it's either +1 or -1. So these are called classification functions, and basically the classification function allows you to map to all possible reals, right? On the other hand, you could have a soft classifier where you directly estimate the posterior, the probability that you are estimating something as y equals 1 given whatever input you saw, okay? So, and then this whole thing, when you compute the sign of it, you subtract the half from it and you get the actual decision +1 or -1. Now, these two are very closely related to each other. In fact, we'll talk about that in a minute. But how do I get the best F or G? Picking the best classifier, soft classifier, or classification function depends on the loss function. Okay? All right. Okay, so these two, I mean, it takes a minute to sort of figure out that if I map to the reals or map to 0-1, they are very easily related to each other, and they're basically related to each other for the sigmoid. All right, any questions so far? Okay. So the reasons these two matter is some people work with probabilities and some others, there's a lot of theory that's been done in this domain over the reals. But having this relationship allows us to map the two of them, all right? So I'm going to talk about one last notion in classification, which is called as margin-based loss, okay, particularly in binary classification. And what that does is it combines your decision f of x, which is your classification decision, and the actual true value y, and puts them together. So you see that when the classifier matches the true label, this will always be positive, right? So the margin, the sign of the margin tells you how right your classification function is about the particular value of x, right? So here's your classic 0-1 loss. For all positive values of the margin, you have no loss, and all negative values of the margin, the loss is 1. Right? This is the one that's hard to implement in practice. One way people get around is they use, say, for example, hinge loss. And this is how hinge loss behaves. It actually starts increasing the weight on the incorrect decisions in a linear manner. Right? The exponential loss increases the weight on the incorrect decisions in an exponential manner. So it's how much you weight those errors, and you can also have the logistic loss, which is in the following form, which slightly differently changes the weight. Okay? The whole point of classification is always, in the margin-based form, it precisely tells you how you're weighting the errors, and then learning the algorithm you learn as a result. Okay? So margin-based loss is a very nice way to look at this whole classification because they synthesize these two things that you need in one form. Okay, so we want to look at, and there's a lot of properties of loss functions in the margin-based form. So I'm going to sort of convert alpha loss to its margin-based form. That's really just a few more minutes of doing this, and then we'll talk about how alpha loss behaves for certain hypotheses classes. Okay? All right, so this is alpha loss. If you go back, I mean, for alpha equals 1, you get log loss. And then for all other alphas, you basically, as soon as you estimate a probability, you raise the probability to this power, scale it by this, and you get this, right? And the limit alpha equals infinity, you get this 1 minus probability of error. So now so effectively, alpha loss acts on these probabilities, and therefore you need what's called a soft classifier. You could also do a classification function, then you would use a sigmoid after that, right? So from now on, we're going to look at soft classifiers as our hypothesis class, okay? And if you want to transform this loss to a margin-based form, you would basically use the sigmoid. So here's the margin-based form. Okay? It's just a detail. You take a classification function, you multiply it by the ground truth, and then this is your loss function. Because the sigmoid has brought it down to the 0, 1, right? That's what you need as a probability. Okay. And you recover all these well-known forms, loss functions that you know of in the margin-based form. Okay, so here's something I want you to pay a little bit of attention to. So you have margin on the x-axis, and you have the loss behavior on the y-axis, right? So for alpha equals infinity, you get as close to the 0, 1 loss. You get the soft 0, 1 loss. You get the sigmoid that behaves in the following way. You get very little, in the limit you go to 0, you get very little penalty for making the right decision, right, which as it should be, and the penalty sort of tapers off to 1 for making a wrong decision. Okay? As you decrease from alpha equals infinity, you still get these quasi-convex shapes until you come to alpha equals 1. And you go down from alpha equals 1, you get more and more convex, which means the penalty for making an error keeps increasing. Okay? Why does this matter? This matters because in the adversarial setting where you have noise, you really don't want to be here because then you're actually boosting those outliers, and therefore you're going to make more errors. So you want to be in the setting where alpha is greater than 1, where you give less penalty to the outliers, and therefore you can be robust. And you also get closer to 0, 1 loss in the process. Okay? On the other hand, when you have these sampling biases or in a class imbalance setting, you want to boost the outliers, which is exactly what exponential loss does in the boosting sense, and therefore you can actually explore. You don't have to restrict yourself to log loss. You can go below alpha equals 1. So first we look at the properties of all this mathematically, and then I'll give you examples where we do better than alpha equals 1 for these different settings. Okay? All right. So bottom line from these plots, alpha less than or equal to 1, this loss function is convex. Alpha greater than 1, the loss function is quasi-convex. Okay? All right. All right, so you have these two perspectives, and I sort of told you this. When you increase alpha, you get robust to outliers. But keep in mind, these curves get flatter and flatter. They get quasi-convex. It's going to be harder to optimize. And I'll tell you exactly how hard it is to optimize formally, right? And on the other hand, for alpha greater than, less than 1, it's pretty convex, and you'll see how it's useful. Okay. So last 2 minutes on classification functions. What makes a good loss? Something a good surrogate loss. Bottom line, something that's a good surrogate loss should behave as well as the 0, 1 loss, right? To put it very loosely. So the 0, 1 loss, you know what the behavior is. It's the Bayes predictor is how you should behave. A good surrogate loss would pretty much agree with the Bayes predictor almost all the time, right? So this notion is called classification calibration, and it can be viewed as what's called a pointwise Fisher consistency. So in the interest of time, I'm not going to go into these mathematical details, but what I can tell you is that these well-known loss functions like 0, 1 log, obviously 0, 1, log loss are already classification calibrated. And now we have a tunable loss function that includes log loss, so the entire class is classification calibrated, okay? Which just means it's actually consistent with 0, 1 loss, okay, in terms of getting the right result. So what I'm going to do in the next half of the talk is look at a particular learning model. Remember, G is our learning model, right? What I pick G, I could pick G as a deep neural network, which is what I would do in practice. But to make my analysis easy, I'm going to start with a particular model for G, and I'm going to understand what's the optimization landscape of alpha loss for this G. All right? So what do I mean by logistic regression? The standard linear regression is where you have a bunch of data points, you fit a line, so then a new data point comes in and you can predict, or you can predict the next data point, right? In logistic regression, you're not predicting over all possible values, you're sort of clustering, you're classifying. So in logistic regression, sometimes this kind of a logistic loss is used, okay? So more formally, the form of logistic regression is you have a bunch of parameters theta, okay? And they belong to a ball of radius r in a d-dimensional space, and your data itself is in a d-dimensional space in the same ball of radius r, right? So let me use this figure to tell you. So here are your data points. You're going to multiply them by these. So you're taking an inner product of your data with this vector theta. you sum it up, and you apply a sigmoid. When you apply a sigmoid, you're restricting yourself to 0, 1, and therefore you have a probability, and then the loss function acts on this probability. Okay? So our goal is, given these x's, you want to be able to predict the feature, the label y, right? So in training, you would use y along with this loss to actually minimize some measure of distance. That's this loss function that you have. And then in test, hopefully this works very well. Okay. So you can, if you put alpha loss in this particular form here, you can expand it and write it out. And then for alpha equals 1, kaboom, you recover cross entropy. Okay? All right. And in learning, there's really two functions of interest. If you knew the statistics of the data, you get the true alpha risk. And when you work with only n samples, you have the empirical alpha risk. The problem of generalization is to figure out how close these two are. We're not going to talk about generalization, but we're going to talk about how the true risk, what's the optimization landscape of the true risk? How hard is it to optimize? Can I get to a solution? To get to this optimization landscape, I'm going to introduce a little bit of theory in this context, and this is the notion of anytime you move away from strictly convex functions, there's this slight weakening that was introduced by Hassan and Shailev Schwartz and so on, and it's called local quasi-convexity or strict local quasi-convexity, SLQC. Right? So we'll go through a little bit of this algebra for a few minutes, and the idea is as follows. All right, you have a local minima theta naught, all right, and theta is any point, okay, and so you have these two constants you need, epsilon and kappa. Okay, so then a function that maps from this d-dimensional space of theta to the set of reals is all these parameters SLQC under the following conditions. So here's our function, right? So you're looking at one minima, which is theta naught. If you are at if your function is within epsilon of this minimum value f of theta naught, you're SLQC. So you're locally quasi-convex right here in this web. Okay. Or you're outside, f values are larger, so your theta is somewhere outside, but the gradient at theta is such that the negative of the gradient is in the same direction as the direction from theta to theta naught. And it's not just for theta naught, this holds true for all points in a ball of radius around theta naught. So this kind of local quasi-convexity allows you to then clarify how many iterations you need on some kind of gradient descent algorithms to get to theta naught. Okay? Okay, all right. So for our problem, f is going to be the expected alpha risk, right? So this is really plotted for some real distributions. It's a two-dimensional Gaussian mixture model, okay, with all these parameters. And this is for alpha equals 1, and this is how my optimization landscape looks. Here's my local minima, which is actually the global minimum in this case. And here's what it looks, and this is our epsilon. So we pick that epsilon, and so that's our plane for the epsilon. If you're below that plane, you're in any theta where your f of theta is below that plane, voila, you're going to go down there, okay? If you're above that plane, in fact, you can do it in less than a certain number of iterations. If you're above that plane, you need at least a certain minimum number of iterations, okay? And if you're above that plane, with respect to all these points in this ball of radius epsilon over kappa, you have this cone from your point, and the direction of the gradient is such that this is true. Okay? Then you're strictly locally quasi-convex. The good point is when you have this strictly locally quasi-convex, you can write out, as I told you, these iterations, and I'll tell you in a minute what that is. And for the special case when your function is strictly locally quasi-convex and you have this, you know exactly what its Lipschitz coefficient is, g, with respect to theta, then you know exactly what the epsilon, for a given epsilon, you know what kappa is. It's the g itself. Okay? All right. Okay, and this is an example of alpha loss for one-dimensional GMM, and it's exactly SLQC. Okay? All right. So the whole point, as I told you, of this notion of introducing SLQC was then Hassan et al. Were able to tell you that for normalized gradient descent, and they've done it for SGD as well, but we'll stick with normalized gradient descent. Normalized gradient descent is as follows. You start with some point theta 1, and the way you're going to update your theta parameter is in the following way. You're going to take the gradient of your function at that theta and then normalize it, and you have an adaptive, you have a rate here eta, which is the same, right? Because this is normalized, you are only using the direction and not the actual value, okay? And then you keep doing this until at some point you stop at t iterations. Okay? So what are the number of iterations you need? It turns out if your function is SLQC, right, to get to within epsilon of your minima, you need at least this many iterations. So the iterations depends on where you start with respect to your minima, and it also depends inversely on epsilon over kappa, which is the radius of that ball around your minima. Okay? Okay, so this is what the theory shows. Let's come back to our setting. And what we want to do is we want to understand how does, so this SLQC is one way to look at how hard is it to optimize alpha loss. Is there a reason people stick with log loss in practice? Maybe because it's easy to find these minima. Is there a reason why we cannot get to 0-1 loss in any practical way? So this theory helps us actually evaluate how hard it is to optimize. All right, so here's our theorem. Our first theorem is, basically we're making an assumption that our expected loss has some critical point. And that's not a hard assumption to make. If this wasn't true, you couldn't do anything with loss functions. All right, so in the regime where we are between, alpha is between 0 and 1, all right, we're actually SLQC with the following parameters. You give me an epsilon, and there's a theta naught, which is my minima. I have this parameter CR alpha, where CR alpha is really the Lipschitz coefficient of this expected loss with respect to the theta parameters. Okay? Okay, so the good news is when alpha is less than or equal to 1, I actually have I know that I need these t iterations, and with, if I do at least that many t iterations, I'll get to a minimum. So it's not very hard. That's a good landscape problem, right? So this explains why exponential loss works. This explains why log loss works. Okay. And the proof basically follows from these quasi-convexity properties. Okay, but what if we increase alpha? Here's our visualization for this two-dimensional GMM. So here's my beautiful convex landscape for alpha equals 1. I go to alpha equals 2, I start seeing my Hogwarts hat come in. It looks like a Hogwarts hat to me. But the range actually gets smaller, and you start seeing these, this is only logistic regression, and you start seeing these kinds of little ruffles that you expect when you see landscapes of deep neural networks. But the interesting part is there exists this really nice little minimum, and if you are close enough, you will fall in there, right? We want to find out how that epsilon and kappa behaves now, right? So here's our theorem. It's realistically not good news. It basically tells you that as you increase alpha from 1, your SLQC parameters get worse. Okay? And how so? In the following manner. We're going to assume that there exists an alpha naught, for example, alpha equals 1, for which you are SLQC. Okay? And you're SLQC with these following parameters. How much worse will you get as you increase from there? First of all, what you can prove is that you are SLQC even as you increase from this alpha naught, which is actually very cool. You still continue to be strictly locally quasi-convex with the following parameters. Epsilon increases linearly with alpha, and LR is really the Lipschitz coefficient, okay, of R alpha with respect to alpha, by the way. And here's the bad news. The radius goes exponentially down in alpha as you increase from alpha naught, okay? And there, the KR is the Lipschitz coefficient of the gradient of your risk with respect to alpha, okay? All right, so here's your visualization of that bad news. What this is telling you is here's where I started, right? I mean, if I was here and I could just go roll into this minimum point, I need at least those t iterations that I talked about. When alpha epsilon increases, effectively means you have to guarantee SLQC for points even higher up. That's one. And the other is the radius is smaller, so my solid angle gets smaller. So it's a harder requirement. The radius is smaller, it means that the number of iterations I need increases. Okay? That makes sense, right? So the way we actually proved this, we wrote an equivalence between the traditional SLQC definitions and a slightly new way of looking at the problem geometrically. So we have a new equivalent. This is the classical SLQC definition, and it basically tells you for all points in the ball, the negative gradient should be in the direction of the descent that you want. And what we can write this as is, with respect to just the minima itself, the negative gradient with respect to the direction of the minima should be at least this much. Sort of like, if you look at the proof, it looks like a reverse Cauchy-Schwarz inequality, right? So this gamma is the radius of the ball itself. Okay, it's coming from there. And then you use a bunch of Lifshitz inequalities, but our proof actually only holds, if you start at an alpha naught, you can only go up to another alpha in a bounded range. So then we bootstrap that proof over and over again, and that's how you get that exponential decay. Okay? So actually, it doesn't look like a good result. It looks bad. But here, I'm not going to give you generalization results, but I'll tell you the following. What I'll tell you is that if you look at the loss for any R alpha, this is the empirical, the true risk, and not the empirical, the true risk, and if you look at the loss for the 0,1 loss, R infinity, it's always bounded by this much. If you had infinite samples, the bound is only some LR divided by alpha. So it's actually going down as 1 over alpha, and what we found in practice is that alpha in a range between 0.8 and 4 works beautifully. You get enough gains, and it gets much harder to actually optimize beyond 4. But you get gains over log loss, so that's sort of what you need, right? There's many interesting problems here. How do you, I mean, the bottom line is I've introduced a new hyperparameter alpha, right, that you have to train over. So how do you find these hyperparameters? You could use our bootstrap algorithm, or you could do some Bayesian optimization and so on. So there's some new problems here that we want to figure out. But let me finish this last part of the talk with some experiments, okay? So what I want to show you is how it behaves when you have noise, or how it behaves when you have class imbalance, all right? So the first is, so in the noisy setting, I'm going to look at two cases. So I'm going to look at two data sets, which is the MNIST data set, which is the digits, and I'm going to look at the CFAR data sets, CFAR 10 data set that has 10 classes. I think it's cat, dog, automobile, airplanes, helicopters, trucks, and so on and so forth. All right, so we considered the standard logistic regression architecture because we obviously have theory for it, but we also went beyond and we looked at a two-layer, meaning two back-to-back CNN pooling, with pooling layers, right, architectures. So that's a CNN2. So the way we do this experiment is we flip a certain fraction of the labels, right? So if you did not flip any labels, what you're seeing here is what is the accuracy of log loss, what's the accuracy of alpha loss, what's the relative gain. And obviously you also see what alpha is maximizing, right? So as you increase the number of labels that are flipped, and you go up to say 20% flipping of labels, you actually get a sufficient gain from increasing alpha. Yeah, you still have 1 and 7. In fact, it's on the entire data set. Okay, so you flip at random something that's not the original. So you take any of the other 9, you pick 1. Very good, uniform random. So we did this also for the 1 and 7s, but we were able to do it for the entire class. Okay. Likewise here, you flip at random out of the other 9. Okay. Okay, so we can do this also for features, and the way we do it for features is actually, we do it at the pixel level. You take a biased coin on each pixel, and I think we did this over a range of probabilities. So you flip a biased label, and the bias is actually the probability at which you're going to flip. And so we took a bunch of values. So if it's heads, you're going to draw a value from a uniform distribution and add it to the pixel. And then it may saturate, and then it may go out of range, you just saturate it, and so on. right? So here again, we looked at MNIST and CFAR, and we look at two architectures for each of them. And the bottom line is that as you increase alpha, in fact, relative to log loss, which is alpha equals 1, you can get significant, at least, it always does better than alpha equals 1. Okay? All right. Finally, in the class imbalance setting, here we took CFAR 10, but what we did was we pulled out two classes. So suppose we actually pulled out dog and cat. So dog was the dominant class, and we made cat 10% of the overall class, overall data set. And we did the same for auto and truck. Because these are very close to each other, you can actually make errors. And I really like the example with the cat and the dog. C1 is the dominant, and C2 is the less frequent class here, okay? It's 91.9%, okay, not 90.10. So you see the relative accuracy. So what's happening here? What would alpha loss do? When you have too few samples, you are going to make an error on the class with fewer samples, right? But because alpha loss actually boosts those outliers, you end up doing better both on that class as well as on the imbalance class as well as on the overall class. Okay? So these are our experimental results so far, and we hope to do more on this. I'm sort of going to leave it at that, right? So I did not present you generalization guarantees, but I gave you some properties, and I showed you how the landscape looks. And we're looking to understand how can we pick the alpha values, how can we exactly apply it to study robustness, perhaps even using some of the techniques that Varun talked about on Monday. And we also want to give these guarantees for DNNs. So for example, what we did here is, here's your data, right? This is a DNN, here's your inputs. This is what we looked at, right? This one particular node is a logistic regression. Now, can I actually stack a bunch of logistic regression and then look at how the SLQC behaves? We have some preliminary results. And then I can both vertically stack and horizontally stack and see how well it does for DNNs. So those are the kinds of things we're looking at. Thank you. And for students, if you're interested, you can always email. I was on time. Why? I don't. So yes. So I'm not doing the standard logistic regression. No, so this is why I introduced this logistic regression formulation, because the way Andrew Ng does it, you can use any log loss with logistic regression. Logistic regression just means that you're going to come up with a probability to do your estimate. In practice, the way people conflate logistic regression is they always use log loss. So I can use any loss, and I'm using alpha loss. Very good question. I cannot tell you the answer. It should change somewhat similar to what you said. So I suspect there is a trade-off. I struggle with how to visualize this. So I don't know. If you have some ideas, you can tell me about it maybe offline. Any other questions? I should use arithmetic mean?
Arithmetic mean. As far as I know, generally in the class imbalance community, arithmetic mean that is scores. But
yeah.
Rather than accuracy, because generally people complain saying that any classifier is good on accuracy. If it is class imbalance system.
It's good on the accurate class.
Use accuracy as a measure. Because arithmetic classifiers can also do well because of class imbalance.
They can do well on which class? Yeah, because it's an average measure. Right. But arithmetic mean of what?
It is that both it is harmonic mean of the two elements.
I see. Okay.
That's known idea. These two are known ideas.
Right, you're right. I mean,
From the so-called confusion matrix, they can
correct.
have these two as a derived performance measures.
Right.
And I have a small comment. I believe that the recent results of Clayton-Schwartz will be valid for your case, where he argues that even if there is a class imbalances, it will be classification calibrated. That is an extension of John Bartlett, Michael Jordan, John Olive, classification calibrated.
What, the loss function will be classification calibrated?
Loss functions can be classification calibrated, even if there are costs too.
Right. So classification calibration is sort of independent of the distribution of the data. It's for every point, for every sample, you want to be Fisher consistent.
Okay, maybe there is a confusion between what both are saying.
Yeah.
I'm meaning that classification calibration in the sense Michael Jordan, Peter Bartlett, and John Olive originally did.
Right, which is this pointwise Fisher consistency.
Townsend result.
I see, okay, but okay, maybe we can talk about it offline. All right. I say, what do you mean by cost? Okay, now okay. All right, we can talk about this offline. Any other questions? I saw one more hand.
Okay.
Thank you.